The monster has awakened. Right now, as you read these words, a dark wound on the surface of the sun stretches wider than 130,000 kilometers across. That's 10 times the diameter of Earth. And it's pointing directly at you. You might think you're safe here, 93 million miles away, protected by Earth's magnetic field and atmosphere. But what makes this moment terrifying isn't the sunspot's size alone, it's that we've seen something almost identical before. In 1859, a sunspot of nearly the same proportions unleashed what scientists now call the Carrington event, the most devastating solar storm in recorded human history. Telegraph lines caught fire. Operators were electrocuted at their stations. The night sky over the Caribbean glowed red with auroras that had no business being there. Now, 166 years later, you're staring at its twin. Here's what keeps scientists awake. In 1859, the world ran on steam and copper wire. Today, your civilization floats on satellites, pulses through fiber optic cables, and breathes through power grids stretching across continents. A Carrington-class event striking tomorrow wouldn't just inconvenience you, it would erase everything. $2 trillion in damage. Blackouts lasting not hours, not days, but years, and it's building energy with every passing hour. Before we go further, let me be honest with you, YouTube's algorithm only shows our videos to people who actually engage with them. So if you're genuinely fascinated by this, if you want to understand the cosmic threats that could reshape your world, then help us reach more people like you. Hit that like button if you're finding this valuable. Subscribe if you want more scientific deep dives that cut through the noise. Ring the notification bell so you never miss when we uncover what the mainstream media won't tell you about space. Your engagement literally determines whether we can keep making these. Now, quick question. Where in the world are you right now? What time is it there? Have you ever seen an aurora with your own eyes? Drop a comment, I read every single one. The sun does not sleep. You think of it as this constant, reliable presence rising each morning, setting each evening with mechanical predictability. But that image is a comforting lie. The reality is far more violent. Beneath that golden disk you see in the sky lies a churning ocean of plasma, a sphere of hydrogen and helium, undergoing constant nuclear fusion at temperatures exceeding 15 million degrees Celsius in its core. On its surface, where temperatures drop to a mere 500 degrees, something strange emerges from time to time, dark patches. Cooler regions where intense magnetic field lines have become so concentrated, so tangled, that they actually inhibit the convective flow of heat from below. We call these sunspots, and they are the birthplaces of chaos. On November 28th, 2024, something extraordinary rotated into view on the sun's eastern limb. Astronomers monitoring their screens noticed a dark region emerging from behind the curve of our star. But as hours passed, it became clear this was no ordinary sunspot. It kept coming and coming. It took more than 2 full days for the entire structure to rotate fully onto the Earth-facing side of the sun. Imagine watching a shadow creep across a wall, except this shadow is larger than Jupiter, and it's emerging on the face of a ball of nuclear fire 93 million miles away. You're watching through instruments capable of resolving details down to 100 kilometers across, and what you're seeing doesn't make sense. The darkness just keeps spreading. When it finally revealed itself in its entirety, the scientific community fell silent. The complex, now designated AR4294 through AR4296, spans an area so vast that NOAA was forced to split it into 3 separate numbered regions simply because their classification systems could not handle its scale. Think about that for a moment. We have sophisticated systems designed specifically to catalogue and track solar activity. Systems built over decades of observation. And this sunspot broke them. 130,000 kilometers of magnetically tortured solar surface, multiple cores, each one the size of Earth, and at its heart, a magnetic configuration so complex that scientists have given it the most dangerous designation possible, beta gamma delta. Let me explain what that means in terms you can actually understand. Every sunspot has a magnetic field. That's what creates them in the first place, magnetic flux tubes rising from deep within the sun's interior, breaking through the surface, and suppressing the normal flow of heat. In a simple sunspot, you have a clear north pole and south pole like a bar magnet. That's an alpha configuration, relatively stable, relatively predictable. But when sunspots grow more complex, when multiple magnetic systems interact and overlap, you get beta configurations regions with both polarities mixed together, already more dangerous, already more likely to produce flares. Add a gamma designation, and you're looking at magnetic field lines that are not just mixed, but intricately intertwined across the neutral line separating opposite polarities. The energy stored in these twisted fields is immense. Think of it like winding a rubber band around your finger tighter and tighter, until the tension becomes unbearable. Now add delta to that classification. Delta means the strongest magnetic gradients regions where opposite polarity fields are pressed together so tightly that they're essentially in contact. Dr. Vasil Yershishin, a solar physicist at the Big Bear Solar Observatory, described it in a 2019 paper as magnetic field lines fighting for the same space. When that happens, when you have opposite polarities forced into such close proximity within a single penumbra, the lighter outer region of a sunspot, the field lines don't simply coexist. They snap, they reconnect, and when they do, the energy release is catastrophic. Beta gamma delta configurations produce the most powerful solar flares we've ever measured, X-class flares, the kind that can be detected on Earth, not just as spikes in radiation, but as actual disruptions to technology. Here's what makes AR4294 uniquely terrifying: its sheer persistence. Most beta gamma delta regions last a few days before either erupting violently or decaying back into simpler configurations. AR4294 has maintained this structure for over a week now, growing more complex, building more energy, like a coiled spring being compressed further and further. Have you ever seen a sunspot through a telescope if you have a safe solar filter and even a modest backyard telescope? You can see them yourself. They look like tiny dark freckles on the sun's face. But AR4294 is visible even without magnification if you project the sun's image safely onto a white card. You can see this monster with your own eyes. When was the last time a sunspot was that large? 2014. Active region 12192. And before that 2003. Halloween storms. Those dates should concern you. The 2003 Halloween storms caused the Swedish power grid to fail for over an hour. They damaged transformers in South Africa. They forced airlines to reroute flights away from polar routes because the radiation levels at altitude became dangerous for passengers and crew. The estimated economic impact exceeded $2 billion. The 2014 sunspot, AR12192, is actually larger than the current AR4294. At its peak, it stretched 140,000 kilometers across the largest sunspot observed in 24 years. Scientists held their breath for 2 weeks as it transited the Earth-facing disk. It produced 6 X-class flares, dozens of M-class flares, and was so active that observers could see its evolution hour by hour. But here's the twist that saved us geometry. Despite all that explosive activity, despite being the most prolific flare producer of solar cycle 24, AR12192 never launched a significant Earth-directed coronal mass ejection. The flares erupted. The radiation surged, but the actual matter, the billions of tons of charged particles, shot off in other directions above the plane of the solar system, below it, anywhere but toward us. Dr. Holly Gilbert, then director of NASA's Heliophysics Division, called it cosmically fortunate. In a 2014 interview, she stated bluntly, "If those CMEs had been Earth-directed, we would have faced the most significant space weather event of the modern technological era. AR4294 could be different. Its magnetic configuration is not just complex, it's unstable. And unlike AR12192, which remained relatively stable throughout its transit, this region is already showing signs of significant activity. Small flares, filament eruptions, the kind of precursor activity that suggests something bigger is building. The question isn't whether AR4294 will erupt. The question is when and in which direction. And right now is pointed straight at you. Over the next several days, this magnetic monster will continue its slow march across the sun's face, carried by the star's 27-day rotation period. Each day it remains Earth-facing is another day we hold our breath. Each hour that passes without a major eruption is simultaneously a relief and an escalation of tension, because the energy doesn't dissipate, it accumulates. But AR4294 isn't alone out there. And what happened on December 1st proved that sometimes the threat you're not watching is the one that strikes first. December 1st, 2024, 4:43 Universal Time. You're not watching AR4294 when it happens? Nobody is, because the explosion doesn't come from the monster everyone's watching. It comes from its neighbour, a region that had already rotated into view days earlier. Dismissed as less threatening, catalogued simply as AR4299, and then the instruments scream. An X1.9- class solar flare erupts with such intensity that detectors aboard GOES 16, the weather satellite stationed 22,000 miles above Earth's equator, register the spike within seconds. The radiation surge is so powerful that it ionizes Earth's upper atmosphere across the entire daylight hemisphere in exactly 8 minutes and 20 seconds, the time it takes light to travel from the sun to your planet. If you're a pilot flying over Australia at that moment, your radio goes dead. Not static, not interference, complete silence. The high-frequency communications that aviation depends on the bands between 3 and 30 MHz that allow planes to talk to ground control across oceanic routes simply stop working. Controllers in Melbourne and Sydney watch their screens as aircraft transponders continue reporting positions, but voice contact is severed. For 30 minutes, you're flying blind in terms of communication. Maritime operators experience the same blackout. Ships in the Coral Sea, the Tasman Sea, vessels navigating the Indonesian archipelago all lose HF radio capability simultaneously. The Australian Maritime Safety Authority later reported the disruption affected an estimated 200 commercial vessels and multiple search and rescue coordination frequencies. This is what an X-class flare does, and this wasn't even from the main threat. Let me explain something crucial about solar flare classification, because understanding this scale is essential to grasping what we're actually facing. Solar flares are categorized by their X-ray brightness measured at Earth. The scale goes A, B, C, M, and X. Each category is 10 times more powerful than the previous one. So an M-class flare is 10 times stronger than a C-class, an X-class is 10 times stronger than an M-class. But here's where it gets interesting. The X-class scale doesn't stop at X1. It keeps going. X2 is twice as powerful as X1. X5 is 5 times as powerful, and we've measured flares exceeding X20. The most powerful flare ever recorded occurred on November the 4th, 2003, an X28 that actually saturated the sensors. Scientists estimate it may have peaked closer to X45. The December 1st flare from AR4294 was X19, significant, but not catastrophic. What made it notable was the source AR4299 had been on the Sun's Earth-facing disk back in November, where it produced a spectacular display of auroras visible across much of the northern hemisphere. Then it rotated to the far side, spending 2 weeks hidden from our view. Now it had returned, rotating back into view from the eastern limb, and it immediately reminded us it was still dangerous. Dr. Ryan French, a solar physicist at the National Solar Observatory, posted on social media within hours, AR4299 is back, and it's not happy about being ignored. He was joking, but the underlying point was dead serious. Active regions don't simply disappear when they rotate out of view. They evolve, they grow, and sometimes they come back angrier than when they left. But flares are only half the story. The radiation reaches Earth in 8 minutes because it travels at light speed. It's the opening salvo, the warning shot. The real danger takes longer to arrive. When those twisted magnetic field lines snap and reconnect during a flare, they don't just emit electromagnetic radiation. They can also launch matter into space. Billions of tons of it. Protons, electrons, and heavier ions accelerated to velocities that can exceed 3000 kilometers per second. We call these eruptions coronal mass ejections, CMEs, and they are the true architects of geomagnetic chaos. Think about what that means for a second. When you see images of solar flares, those brilliant arcs and loops of plasma, you're looking at magnetic field lines made visible by superheated gas. When a CME erupts, you're watching actual chunks of the Sun's atmosphere being hurled into space. Not radiation, not energy waves, physical matter. The equivalent of 1 billion nuclear bombs worth of material travelling at speeds that would cross the distance from Earth to the Moon in less than 3 hours. AR4299's December 1st flare did produce a CME, but it was directed slightly off-axis from Earth. The geometry wasn't quite right. We caught the edge of it a glancing blow that produced minor geomagnetic disturbances, but nothing significant. The flare's radiation effects were short-lived. The radio blackout lasted 30 minutes. Satellite operators noted the event and moved on. But 5 days later, AR4299 spoke again. December 6th, 2024. This time the flare measured M8, one just shy of X-class but still formidable. On a logarithmic scale where M9 transitions to X1 and M8, one is roughly 80% of the way there in terms of energy output. More importantly, this time the explosion launched a full halo CME. When solar physicists see a halo CME in their data, they pay attention. The term halo refers to how the CME appears in coronagraph images from spacecraft like SOHO, the Solar and Heliospheric Observatory. A coronagraph blocks out the Sun's bright disk so you can see the fainter corona surrounding it. When a CME erupts directly toward Earth, it expands outward from the Sun in all directions from your perspective, creating a circular halo effect around the occulting disk. A halo CME means it's headed straight for you. NOAA's Space Weather Prediction Center analysed the coronagraph data and calculated the CME's velocity 143 kilometers per second. That's 2.5 million miles per hour. At that speed, the leading edge of this billion-ton cloud of charged particles would cross the 93 million-mile gulf between Sun and Earth in approximately 36 hours. The forecast was issued within 6 hours G3-level geomagnetic stormwatch for December 8th and 9th. Let me put that in perspective. Geomagnetic storms are rated on a scale from G1 to G5, where G1 is minor and G5 is extreme. We've only seen 2 G5 storms in the past 20 years, the Halloween storms of 2003 and the May 2024 event that caused spectacular auroras as far south as Mexico and northern Africa. A G3 storm is classified as strong, not catastrophic, but significant enough to cause voltage irregularities in power systems, require corrections to satellite orientation, and produce auroras visible at mid-latitudes. The storm arrived on schedule. As the CME slammed into Earth's magnetosphere, the impact compressed our planet's protective magnetic bubble like a fist squeezing a water balloon. The solar wind pressure jumped from a baseline of around 2 nanopascals to over 15. Ground-based magnetometers at stations from Alaska to New Zealand recorded the disturbance sharp. Dramatic swings in the magnetic field strength that correlate directly with electrical currents flowing through Earth's upper atmosphere and, frighteningly, through the ground itself. These ground-induced currents are what threaten power grids, but we'll get to that. For now, what matters is this AR4294 fired twice in 5 days, launching a direct hit CME that proved our vulnerability is not theoretical. It's happening right now. And that region, as dangerous as it proved to be, is a smaller, simpler cousin to AR4294. The giant has been watching, learning, building energy. And unlike AR4299, which announced its return with immediate eruptions, AR4294 has been patient, ominously patient. Which brings us to a question that should make you deeply uncomfortable. What happens when magnetic field lines finally snap inside a beta-gamma-delta region 10 times more complex than the one that just struck us? To answer that, we need to understand the physics of annihilation itself. Imagine holding 2 magnets in your hands. When you bring the north pole of one close to the south pole of another, they snap together with surprising force. That attraction is magnetic field lines connecting, flowing from one pole to the other in smooth, orderly curves. Now try pushing 2 north poles together. They resist. The field lines bend away from each other, creating an invisible barrier that you can actually feel pushing back against your fingers. This is magnetic pressure. And in the Sun's atmosphere, where magnetic fields can be 10,000 times stronger than the magnets on your refrigerator, that pressure becomes a physical force capable of suspending billions of tons of plasma against gravity itself. But here's what makes solar flares possible. Magnetic field lines want to be simple. They want to flow in the smoothest, shortest paths possible between opposite poles. When they get twisted and tangled, stretched into complicated geometries by the sun's differential rotation and convective turbulence, they store enormous amounts of energy, like rubber bands wound tighter and tighter around a pencil. Eventually, something has to give. The process is called magnetic reconnection, and it's one of the most powerful energy release mechanisms in the universe. Dr. Nikki Fox, administrator of NASA's Science Mission Directorate, described it in a 2018 interview as the cosmic equivalent of cutting a bundle of stretched rubber bands simultaneously. When magnetic field lines of opposite polarity are forced close enough together, they can suddenly snap and reconnect in a new configuration, one that's simpler and contains less stored energy. Where does that energy go into the plasma surrounding the reconnection site? In a fraction of a second, sometimes as little as 10 milliseconds, particles are accelerated to near light speeds. Temperatures spike from the corona's baseline of 1 million degrees Celsius to over 10 million degrees in the reconnection region. And the stored magnetic energy, which could be equivalent to millions of nuclear weapons, gets converted into kinetic energy, thermal energy, and electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This is what you're seeing when you observe a solar flare magnetic annihilation made visible. The flare itself manifests as a sudden brightening in the sun's atmosphere. If you could watch in real time through an H-alpha filter which isolates the red wavelength of light emitted by hydrogen, you'd see bright ribbons suddenly appear in the chromosphere, tracing the footpoints where magnetic field lines are anchored to the solar surface. These ribbons mark where streams of accelerated electrons are slamming back down into the denser layers of the sun, heating the gas to incandescence. Above these footpoints, in the corona, you'd see loops of plasma suddenly glow and expand as they're heated and inflated by the reconnection process. And if the eruption is powerful enough, you'd see something else, a massive bubble of plasma and twisted magnetic field lines being hurled away from the sun entirely. That's your CME, and unlike the flare's radiation, which dissipates as it spreads through space, a CME carries its magnetic field with it frozen into the moving plasma like fossils preserved in amber. This is crucial to understanding why CMEs are so dangerous to Earth. When a billion-ton cloud of magnetized plasma traveling at 1000 kilometers per second collides with Earth's magnetosphere, it doesn't just bounce off, it interacts. The magnetic field embedded in the CME can have either a north or south orientation relative to Earth's magnetic field. If it's pointing north, matching Earth's field orientation on the day side, the interaction is relatively benign. The fields push against each other like those North Pole magnets in your hand, and the CME mostly flows around Earth's protective bubble. But if the CME's field is pointing south opposite to Earth's northward pointing field on the day side, something dramatic happens. The opposing field lines reconnect, just like they did at the Sun. Earth's magnetic field lines, which normally form a closed shield around the planet, suddenly get peeled open on the day side and stretched back into a long tail on the night side. Solar wind particles that would normally be deflected suddenly gain direct access to the upper atmosphere. They stream down magnetic field lines toward the poles, colliding with oxygen and nitrogen molecules at altitudes between 100 and 400 kilometers. Those collisions produce auroras, the northern and southern lights. Oxygen emits green light at lower altitudes and red at higher altitudes. Nitrogen produces blue and purple hues, but auroras are just the visible symptom. The real danger lies in what you can't see. When geomagnetic storms disturb Earth's magnetic field, they create electrical currents flowing through the ionosphere, the electrically conducting layer of the upper atmosphere between 60 and 1000 kilometers altitude. These currents generate their own magnetic fields, which fluctuate rapidly during storm conditions. And according to Faraday's law of electromagnetic induction, a changing magnetic field induces electrical currents in any conductor it passes through, including the ground beneath your feet. These geomagnetically induced currents, GICs, flow through the Earth's crust, following paths of least resistance through rock layers, groundwater, and critically, through the extensive networks of conductive infrastructure humans have built: pipelines, telecommunication cables, railway tracks, and most importantly, high-voltage power transmission lines. Do you live near high-voltage transmission towers? Those massive steel structures carrying power lines across long distances during a severe geomagnetic storm. Those lines can act like giant antennas, picking up the fluctuating magnetic field and converting it into electrical current. But here's the problem. Power grids are designed to carry alternating current at 50 or 60 Hz. GICs are quasi-DC currents, direct current or very low frequency that the grid's protective systems weren't designed to handle. When GICs flow into a power transformer, the equipment that steps voltage up or down between different parts of the grid, they cause something called half-cycle saturation. The transformer's magnetic core, which normally operates in a balanced state, gets pushed into magnetic saturation during one half of the AC cycle. This causes several catastrophic effects: dramatically increased heat generation, harmonic distortion that can damage other equipment, and production of stray magnetic flux that can heat nearby metallic structures. A transformer experiencing sustained GIC levels above 50 to 75 amperes per phase can suffer permanent damage in minutes to hours. And here's the terrifying reality: we don't manufacture large power transformers in North America anymore. The lead time to order and install a replacement for a damaged, high-voltage transformer can be 12 to 24 months under normal conditions. If hundreds of transformers fail simultaneously across multiple continents, as could happen during a Carrington-class event, the replacement queue could stretch into years. Dr. John Kappenman, a leading expert on geomagnetic storm impacts, testified before the U.S. Congress in 2008 that a severe space weather event could leave 130 million people without power for years, not days or weeks. The economic impact of his worst-case scenario exceeded $2 trillion in the first year alone. With recovery taking 4 to 10 years, that analysis was done in 2008. Our dependence on electrical infrastructure has only deepened since then. But destruction of the power grid isn't the only threat. CMEs carry something else that should concern you high-energy protons. When magnetic reconnection occurs at the Sun, some particles are accelerated to relativistic speeds fast enough that they arrive at Earth in minutes to hours, well ahead of the main CME body. These solar energetic particles, or SEPs, can penetrate spacecraft, damage electronics, corrupt computer memory, and even pose radiation hazards to astronauts and high-altitude aircraft passengers. The Halloween storms of October 2003 produced such intense SEP radiation that NASA temporarily lost contact with the Mars Odyssey orbiter. Instruments aboard Earth-orbiting satellites degraded or failed. Airlines rerouted 26 polar flights to lower latitudes to reduce passenger radiation exposure. And those storms came from a sunspot smaller and less complex than AR4294. So when you look at this magnetic monster currently facing Earth, with its beta-gamma-delta configuration and multiple Earth-sized cores, you're not just looking at a large dark spot on the Sun. You're looking at a loaded weapon. The energy is there. The magnetic tension is building. The configuration is unstable. The only questions are when it will fire and whether we'll be in the crosshairs when it does. And to understand just how devastating that shock could be, we need to look back at the day the telegraph wires caught fire. September 1st, 1859. Redhill, Surrey, England. Richard Carrington is a 33-year-old British astronomer, wealthy enough to maintain his own private observatory, meticulous enough to have spent years mapping sunspot positions with extraordinary precision. On this particular Thursday morning, he's doing what he does every clear day, projecting an 11-inch diameter image of the Sun onto a screen in his darkened observation room, carefully sketching the sunspots visible on its surface. At 11:18 a.m., something happens that no human has ever witnessed before. 2 intensely bright patches of white light suddenly appear within a large sunspot group. Carrington later describes them as 2 patches of intensely bright and white light that erupt side by side within the darker umbra. The brilliance is so unexpected, so unprecedented, that he doubts his own eyes. He rushes out of the room to find anyone who can confirm what he's seeing. By the time he returns with a witness less than 60 seconds later, the lights are already fading. The entire event lasts approximately 5 minutes. Carrington has just observed the first solar flare ever recorded in human history. But he has no idea what he's seen. He doesn't know that 93 million miles away, magnetic field lines have just annihilated each other with the force of millions of hydrogen bombs. He doesn't know that a wave of electromagnetic radiation is already racing toward Earth at light speed. And he certainly doesn't know that 17 hours later, the night sky will catch fire. Do you wonder what he thought in that moment standing there in his observatory, having just witnessed something impossible? Something that shouldn't exist according to the understanding of the time he writes in his notes, that the phenomenon was so very unusual that he felt compelled to call a witness to verify it. That restraint, that scientific caution, is remarkable considering he's just seen the sun explode, September 2nd, 1859, just after midnight, across the entire planet, from the Arctic Circle to the tropics. The sky erupts in colour. Auroras blaze across the heavens in shades of red, green, white, and crimson that eyewitnesses struggle to describe. But these aren't confined to the polar regions where auroras normally appear. They're visible in Cuba, in Hawaii, in Colombia and Jamaica, in Central Africa, in the Bahamas. A ship's captain records in his log the whole sky appeared mottled red, as if in flames. In Panama, observers report the southern horizon glowing blood red for hours. Perhaps most dramatically, in the Rocky Mountains, gold miners wake in their camps convinced that dawn has arrived. They begin preparing breakfast, heating coffee, discussing the day's work until they check their pocket watches and realize it's 10 a.m. The aurora is so bright they mistook it for sunrise. In northeastern U.S. cities, people read newspapers outdoors by aurora light alone. In Boston, a journalist writes that the illumination was sufficient to read ordinary print. In Baltimore, the aurora is described as being so brilliant that ordinary print could be read by its light at midnight. These aren't vague accounts or exaggerations. These are specific, documented observations from educated witnesses who understood they were seeing something extraordinary. But beauty masks destruction. Telegraph systems, the cutting-edge technology of 1859, the Victorian equivalent of the internet, go haywire across 2 continents. In Washington, D.C., telegraph operator Frederick Royce is working the line to Richmond when his equipment begins sparking violently. He later testifies that he disconnected the batteries powering his system entirely, and yet the telegraph continued operating, powered solely by the electrical currents induced by the geomagnetic storm. Think about that. The equipment is functioning without its power source, running on electricity pulled directly from the disturbed magnetic field of Earth itself. Telegraph operators in Boston report receiving severe electrical shocks when they touch their equipment. In Norway, telegraph machines catch fire. In Sweden, the equipment produces such strong currents that operators have to disconnect the systems to prevent injury. Messages that should take minutes to transmit take hours as operators work around the interference, or become impossible to send at all as the induced currents overwhelm the weak battery-powered signals. Some operators discover that by disconnecting their batteries and grounding their lines properly, they can actually improve communication. The storm is providing more power than their batteries can. In a remarkable demonstration of improvisation, telegraph operators in Boston and Portland, Maine, conduct a 2-hour conversation powered entirely by auroral currents. But the damage is real. Telegraph companies estimate losses in the tens of thousands of dollars, millions in today's currency. The New York Times runs a story on September 3rd with the headline, "Extraordinary Effect of the Aurora Borealis on the Telegraph Wires." The article catalogues the chaos. The line was much disturbed throughout the day. Sparks could be drawn from the wires. Violent and long-continued shocks. The question that should haunt you is this: what would that same storm do to our world? In 1859, the entire technological infrastructure of human civilization consisted of telegraph wires and the nascent railway systems. The most sophisticated electrical device most people owned was a pocket watch. There were no power grids, no satellites, no GPS, no internet, no cell phone networks, no computerized anything. The Carrington event caused spectacular light shows and damaged what little electromagnetic technology existed. The same storm striking in 2024 would be apocalyptic. Scientists have spent decades trying to quantify exactly how powerful the Carrington event was. Ice core data from Greenland and Antarctica provide a record during major solar events. High-energy particles create isotopes of beryllium-10 and carbon-14 that get trapped in ice layers. By measuring these isotopes in ice corresponding to 1859, researchers can estimate the intensity of the storm. The results are sobering. A 2012 study published in Space Weather by Dr. Ying Liu of the National Space Science Center estimated that the Carrington CME travelled at approximately 500 km per second, among the fastest ever recorded. The geomagnetic disturbance it produced had an estimated density index of -850 nanoteslas or lower. For context, the May 2024 storm that produced auroras visible in Mexico registered around -412 NT. The March 1989 storm that blacked out Quebec measured -589 NT. Carrington was nearly 50% more intense than anything we've measured in the modern era. But here's what keeps researchers awake. Carrington wasn't even the strongest storm on record. Ice core evidence reveals an even more powerful event occurred in 774 AD, the Miyake event, which produced isotope signatures indicating it was perhaps 10 times more powerful than Carrington. In 1859, nobody measured it because measurement technology didn't exist. In 774, nobody recorded it because there was no technology to damage. Dr. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, stated in a 2013 interview, "If the Carrington event happened today, it would be like a hurricane, a tornado, an earthquake, and a financial crisis all happening simultaneously on a global scale. We would be knocked back to a pre-industrial state in a matter of days. Compare the sunspot that triggered Carrington to AR4294. Historical records describe the 1859 sunspot group as being visible to the naked eye approximately the same size as the current active region. Sketches from multiple observers show a complex multi-chord structure spanning roughly 130,000 kilometers. The magnetic configuration, based on the characteristics of the flare and subsequent CME, was almost certainly beta-gamma-delta. We are staring at a nearly identical twin, the same size, the same complexity, the same Earth-facing geometry. The only difference is the world beneath it. In 1859, the Carrington event was a natural wonder that damaged telegraph wires. In 2024, it would be a civilization-ending catastrophe. And the uncomfortable truth is this: AR4294 has been quiet for too long. The energy continues building. The magnetic tension continues increasing. The longer it remains unstable without erupting, the more energy accumulates in those twisted field lines. When it finally releases, the eruption won't be gradual, it will be catastrophic. But let's be specific about what catastrophic actually means in practical terms, because the nightmare scenario isn't science fiction, it's engineered reality, and we know exactly how it unfolds. Let's walk through what happens when a Carrington-class CME strikes Earth in 2024. Not speculation, not worst-case fantasy, the actual sequence of events based on engineering analysis, government reports, and infrastructure vulnerability assessments. Hour 0, 11:17 a.m. Eastern Time. You're sitting at work when every GPS-dependent system on the planet simultaneously begins reporting incorrect positions. Your phone's map application shows you 3 blocks away from where you actually are. Commercial aviation computers display aircraft positions that are wrong by hundreds of meters. The precision agriculture systems that farmers rely on for planting suddenly can't determine field locations accurately. Automated cargo ships in the mid-Atlantic start veering off course as their navigation systems feed them corrupted data. This is the solar energetic particles arriving the advance guard of high-energy protons that outran the main CME. They're disrupting satellite electronics, flipping bits in computer memory, degrading solar panels, and most critically, interfering with the GPS satellite constellation orbiting 12,550 miles above Earth. The Federal Aviation Administration receives reports from 4,200 aircraft simultaneously. Commercial flights over the Atlantic and Pacific where there's no ground-based navigation backup are ordered to divert to the nearest airports immediately. Within 30 minutes, global air traffic is grounded. The last time this happened was September 11th, 2001. But this is just the opening act. Hour 1, 12:23 p.m. Eastern Time. The CME's leading edge collides with Earth's magnetosphere. The impact is detected by the DSCOVR satellite stationed at the L1 Lagrange point, 1 million miles from Earth in the direction of the Sun. Its magnetometer readings spike. The interplanetary magnetic field jumps from 5 nanoteslas to over 60 NT in less than a minute. And critically, the field is pointing south, the worst possible orientation. Earth's magnetic field lines begin reconnecting with the CME's field on the day side of the planet. The magnetosphere compresses, and massive electrical currents begin flowing through the ionosphere. Within minutes, these currents induce ground currents in power transmission lines across North America, Europe, and Asia. The PJM interconnection, the power grid serving 65 million people across 13 U.S. states, detects abnormal harmonic distortion at multiple substations. Grid operators watch their screens as transformer temperatures begin climbing. In Ontario, the Hydro One system that supplies power to 1.4 million customers shows similar warnings. In the United Kingdom, national grid operators see reactive power demands surging as transformers struggle with the quasi-DC currents flowing through their windings. They have a decision to make: keep the grid online and risk catastrophic transformer damage, or execute controlled blackouts to protect the infrastructure. Most operators choose to shut down sections of the grid preemptively, hoping to prevent worse damage. Have you ever experienced a blackout that lasted more than a few hours? What was that like? Now imagine that blackout extending not for hours, but for weeks or months across entire continents. Hour 3, 2:47 p.m. Eastern Time. Major metropolitan areas across the mid-latitudes go dark. New York City, London, Tokyo, Berlin, Beijing. Not because grid operators didn't act, but because in some regions they acted too late. High-voltage transformers at critical substations have already entered thermal runaway. Internal temperatures exceed design limits. Insulation begins breaking down. In some cases, transformer tanks rupture, spilling thousands of gallons of mineral oil that ignites, sending thick black smoke over urban areas. The North American Electric Reliability Corporation's worst-case analysis, published in 2010, estimated that a severe geomagnetic storm could destroy or severely damage over 300 large transformers in the United States alone. Each one weighs between 200 and 400 tons and costs $3 to $7 million to replace. And here's the nightmare: we don't stockpile these transformers. They're custom-built to order, with manufacturing lead times of 12 to 18 months under normal circumstances. When you lose one transformer, you can reroute power and bring in a replacement. When you lose 300 simultaneously, across multiple countries, with every utility company in the world competing for the same limited manufacturing capacity, the replacement timeline stretches into years. You're sitting in darkness now. Your phone still has battery, but cell towers are losing backup power. Internet service goes down as data centers drain their emergency generators. Natural gas pumping stations, which require electricity to operate, begin shutting down, cutting heat to millions of homes. Water treatment facilities switch to backup power, but those generators have fuel for perhaps 48 to 72 hours. Day 1, September 3rd, 2024. Grocery stores have been picked clean. The modern just-in-time supply chain system that keeps shelves stocked depends on computerized logistics, refrigerated transportation, and electrical infrastructure at every step. Without power, refrigerated goods spoil within hours. Without functioning payment systems, because credit card readers and ATMs don't work, stores that still have goods can't sell them except for cash, which most people don't carry anymore. Hospitals are operating on emergency backup power, but they're designed to run critical systems only operating rooms, ICUs, emergency departments. The generators weren't sized to power entire facilities indefinitely. And the fuel deliveries they need to keep those generators running, those trucks need working gas stations, which need electricity to pump fuel. A 2008 report by the National Academy of Sciences titled Severe Space Weather Events Understanding Societal and Economic Impacts estimated that the cascading failures from a Carrington-class event would affect 130 million Americans within the first 24 hours. The economic impact in the first year alone would range between $1 and $2 trillion. The full recovery timeline, 4 to 10 years. Dr. John Kappenman, who authored much of that analysis, emphasized in congressional testimony that this isn't a technical problem, it's a manufacturing bottleneck problem. He stated, "The vulnerability is not that we don't know how to protect transformers. The vulnerability is that we haven't done it, and now we don't have enough spare equipment or manufacturing capacity to recover quickly when they fail. Week 1, communications networks have degraded to pre-1900S levels. Landlines still work in some areas, but cell networks are down. The internet, which depends on powered infrastructure at every node, is largely offline. The few satellite communication systems still functioning are overwhelmed and reserved for emergency services. Urban areas face critical water shortages as treatment plants exhaust their backup power. Sewage systems begin backing up. In summer months, heat-related deaths spike in regions without air conditioning. In winter scenarios, hypothermia becomes widespread. The social fabric begins tearing. Police and emergency services, overwhelmed and operating with degraded communications, struggle to maintain order. Reports of looting and civil unrest multiply. The National Guard is mobilized in multiple states, but coordinating large-scale responses without modern communications proves nearly impossible. Month 1. The scope of the disaster is now fully apparent. Satellite imagery from these satellites still functioning shows entire regions of North America, Europe and Asia in near total darkness at night. The economic damage assessment continues climbing supply chain disruption, lost productivity, infrastructure replacement costs, emergency response expenditures. Insurance companies, which exclude most geomagnetic storm damage from standard policies, face potential insolvency from the sheer scale of claims. Lloyd's of London published a report in 2013 estimating insured losses from a Carrington-class event at $600 billion to $2.6 trillion. But those estimates assume functional insurance systems and financial markets, which require, you guessed it, electrical infrastructure to operate. The grim reality is that we've built a civilization utterly dependent on electrical technology without seriously considering what happens when that technology fails simultaneously across the entire planet. And unlike a regional disaster, a hurricane, earthquake, or even a large-scale terrorist attack, there's no unaffected area to send aid from. Everyone is hit at once, 6 months later, in the most optimistic scenarios where governments immediately mobilized all resources toward grid reconstruction, where international cooperation functioned smoothly, where supply chains adapted quickly in major urban areas are just beginning to see partial power restoration. Rural areas remain dark. Entire industries have collapsed. The global economy has contracted by an estimated 20 to 30%. This isn't science fiction. This is engineering reality. Every step of this cascade is documented, modelled, and understood by the small community of researchers who study space weather impacts. But here's the question nobody wants to ask loudly if we know this is possible. If we know the sun has produced events like this before and will again, why haven't we prepared? And more urgently, given that AR4294 is active right now, what's actually being done to protect us at this very moment? The answer is remarkably little. And what makes this truly disturbing is that it's not because we lack the technology or understanding. It's because protecting against solar storms doesn't win elections, doesn't generate quarterly profits, and doesn't capture headlines until after disaster strikes. Let me show you exactly what's happening right now as AR4294 transits across the sun's Earth-facing disk. NOAA's Space Weather Prediction Center in Boulder, Colorado. The organization responsible for monitoring solar activity and issuing forecasts operates with an annual budget of approximately $25 million. For context, that's less than the cost of a single F-35 fighter jet. With those limited resources, they're tracking AR4294 using data from a handful of satellites and ground-based observatories. The primary space-based asset is the Solar Dynamics Observatory, launched in 2010, which captures high-resolution images of the sun every 12 seconds across multiple wavelengths. SDO cost $850 million to build and launch a significant investment, but it's now 14 years into what was designed as a 5-year mission. Its instruments are degrading. There's no replacement currently funded. The DS-Kovar satellite, which provides the critical 15 to 60-minute warning when a CME is about to strike Earth, was launched in 2015 using a satellite originally built in 1998. It was literally sitting in storage for 17 years before someone decided to dust it off and finally launch it. Discover is now operating years beyond its design lifetime, and it's back up. There isn't one ready. When Discover fails, not if, but when we lose our only deep space early warning capability, think about that. The system protecting your civilization from multi-trillion-dollar damage operates with no redundancy and no concrete replacement plan. But the satellite situation is just one part of a much larger failure of preparation. The real scandal is what's happening, or rather, not happening on the ground. Here's something most people don't know. Protecting power transformers from geomagnetic storms is not technically difficult. The solution is called a neutral blocking device or geomagnetic disturbance GMD protection system. It's essentially a sophisticated capacitor that blocks the quasi-DC currents induced by geomagnetic storms while allowing normal AC power to flow. These devices cost between $40,000 and $200,000 per transformer. Depending on size and voltage class, installing GMD protection on the roughly 2,000 highest risk transformers in the United States would cost an estimated $500 million to $1 billion total. That's the cost of hardening the most critical points in the grid, the extra high voltage transformers whose failure would cause cascading blackouts affecting tens of millions of people. For comparison, Americans spend approximately $2 billion on Halloween candy each year. We spend $11 billion annually on bottled water. The federal government spent $1.7 trillion on defense in 2023. How much was allocated to protect the power grid from space weather? According to a 2023 Government Accountability Office report, the Department of Energy's grid modernization programs had distributed only $62 million specifically for GMD mitigation across all utilities and all infrastructure projects since 2018. That's roughly 6% of what's actually needed, spread over 5 years. Do you want to know why? Because utility companies operate under regulatory frameworks that don't mandate space weather protection, and spending money on prevention doesn't show up as profit on quarterly earnings reports. As long as a catastrophic event hasn't happened yet, utilities have little financial incentive to prepare for one. It's what economists call a tragedy of the commons, individual rational actors making decisions that collectively lead to disaster. In 2019, President Trump issued an executive order titled Coordinating National Resilience to Electromagnetic Pulses. It acknowledged the threat and directed federal agencies to assess vulnerabilities and develop mitigation strategies. The resulting reports, published in 2020 and 2021, confirmed everything researchers had been saying for decades. The grid is vulnerable. The economic consequences would be catastrophic, and we need to invest in protection. Then those reports were largely filed away and forgotten. The Federal Energy Regulatory Commission did issue new reliability standards in 2019 requiring utilities to develop plans for operating during geomagnetic disturbances. But here's the catch: the standards require planning, not actual physical protection. Utilities must have procedures for how they'll respond during a storm, but they're not required to install the hardware that would actually prevent transformer damage. It's like requiring people to have evacuation plans for hurricanes, but not allowing them to build hurricane-resistant structures. The plan matters, but it's not sufficient. Meanwhile, other nations aren't doing much better. The United Kingdom's national grid has implemented some GMD monitoring and operational procedures, but only a small fraction of their transformers have physical protection. Canada, which experienced the 1989 Quebec blackout firsthand, has made more progress than most Hydro-Quebec invested heavily in GMD protection after losing power to 6 million customers for 9 hours. But even their system isn't fully hardened. China, despite having one of the world's largest and most rapidly growing power grids, publicly discusses space weather as a concern but provides little transparency about actual mitigation measures. Japan, sitting at higher magnetic latitude and thus more vulnerable, has implemented some protections but not comprehensively. The pattern is consistent worldwide: acknowledge the threat, conduct studies, issue reports, implement modest measures, then wait for budgets and attention to drift to more immediate concerns. But there's another dimension to this that's even more troubling. We're not just unprepared to prevent damage, we're unprepared to recover from it. Remember those 200 to 400 ton high voltage transformers, the ones with 12 to 18 month manufacturing lead times? The United States currently maintains a strategic petroleum reserve underground storage of 714 million barrels of crude oil as protection against supply disruptions. The reserve costs roughly $20 billion to maintain. We have no equivalent strategic transformer reserve, zero. If 300 transformers fail simultaneously, utilities will be competing for manufacturing capacity with every other affected utility worldwide. The actual replacement timeline could be 5 to 10 years, not because we lack the technical knowledge to build transformers, but because we lack the manufacturing infrastructure to build 300 of them simultaneously. A 2012 joint study by the Electric Power Research Institute and the Department of Energy proposed creating regional stockpiles of critical spare transformers that could be rapidly deployed after a major event. The estimated cost $200 to $500 million for a comprehensive national reserve. That recommendation is now 12 years old. The strategic reserve still doesn't exist, Doctor. William Murta, who serves as program coordinator at NOAA's Space Weather Prediction Center, stated in a 2021 interview, "We know what needs to be done. The technology exists. The problem isn't scientific or technical, it's coordination, funding, and political will. No single entity is responsible for space weather preparedness, so everyone assumes someone else is handling it." So as AR4294 continues its slow rotation across the sun's face, as magnetic energy continues building in its twisted field lines, What's actually being done to protect you satellite operators are monitoring solar activity and preparing to put spacecraft into safe mode if a major flare erupts. Airlines are reviewing their polar route procedures in case they need to divert flights. Grid operators have their space weather playbooks open, ready to implement operational procedures if forecasters issue high-level warnings. These are all reactive measures, damage control, not prevention, and none of them address the fundamental question when AR4294 finally erupts with a Carrington-class CME. Will those operational procedures be enough, or will we join the long list of civilizations throughout history that ignored warnings until disaster forced them to learn the hard way? But perhaps the most unsettling aspect of this entire situation isn't what we don't know. It's what we're deliberately not being told. There are 5 critical facts about solar storm preparedness that government agencies, utility companies, and scientific institutions consistently downplay or omit entirely from public discussion. Not because these facts are classified, not because they're uncertain, but because acknowledging them openly would force uncomfortable questions about responsibility, liability, and the massive gap between what we should be doing and what we're actually doing. Let's start with the most shocking one. Secret number 1. We have almost no warning capability for CMEs originating from the far side of the Sun. Right now, as you listen to this, you can see roughly 50% of the Sun's surface from Earth. The other 50% is hidden on the far side, rotating toward us at approximately 14 degrees per day. Active regions on that far side regions potentially as dangerous as AR4294 are completely invisible to our primary monitoring satellites. We have exactly 2 spacecraft with any capability to observe the far side NASA's Stereo A satellite and the ESA NASA Solar Orbiter. Stereo A orbits the Sun ahead of Earth, providing a view of the eastern limb before regions rotate into Earth view. But its twin, Stereo B, lost contact in 2014 and was never replaced. We lost our western limb coverage, our ability to see active regions before they disappear around the back of the Sun. Solar Orbiter, launched in 2020, does occasionally provide off-axis views of the Sun's far side, but its orbit wasn't designed for continuous far-side monitoring. Most of the time, it's looking at the Sun from angles that don't give us the perspective we need. What this means practically, if a massive active region develops on the far side, grows into a beta-gamma-delta monster, and erupts with an Earth-directed CME just before rotating out of view, we would have 0 warning. The first indication would be when it slams into our magnetosphere, approximately 18 to 36 hours later. Dr. Janet Luhmann of UC Berkeley, a stereo mission scientist, stated in a 2019 paper, "The loss of Stereo B created a critical blind spot in our space weather monitoring architecture. We're essentially trying to forecast potentially civilization-threatening events, while only able to see half the threat at any given time." NASA has proposed a Lagrange point mission, placing satellites at the L4 and L5 points that orbit 60 degrees ahead and behind Earth, which would provide continuous far-side coverage. The proposal has been sitting in budget requests since 2016. It remains unfunded. Secret number 2. Most power grid operators have no physical protection against transformer damage. We talked about GMD blocking devices earlier, but here's what utilities won't tell you directly. The vast majority of high-voltage transformers in North America, Europe, and Asia are completely unprotected. The 2023 GAO report found that fewer than 5% of at-risk transformers have any installed geomagnetic disturbance mitigation hardware. 5%. The rest rely entirely on operational procedures monitoring forecasts, reducing power flows during storms, potentially implementing controlled blackouts. These procedures can reduce damage in moderate storms. But during a Carrington-class event, the induced currents would be so intense that operational measures alone would be insufficient. the choice becomes shut down the grid preemptively for days or weeks based on forecasts that might be wrong, or risk catastrophic transformer damage. Neither option is acceptable. Yet those are the only options currently available for 95% of the grid infrastructure. Utility executives know this. Regulators know this. But there's no political or financial incentive to acknowledge it publicly because doing so might trigger liability concerns or customer anxiety. Secret number 3. Insurance doesn't cover this. Pull out your homeowner's insurance policy. Read the exclusions section carefully. You'll find something about geomagnetic events or solar storms buried in there, typically grouped with other cosmic threats like meteor impacts. Most standard insurance policies explicitly exclude damage caused by geomagnetic disturbances. Business interruption insurance also excluded. Property damage from power surges caused by geomagnetic storms excluded. The insurance industry learned from smaller events that space weather damage could be catastrophically expensive and systematically wrote exclusions into policies. Lloyd's of London published an analysis in 2013 estimating that, even with exclusions, residual insured losses from a Carrington-class event could exceed $600 billion, enough to threaten the solvency of multiple major insurers. Their recommendation was that governments should treat space weather like other catastrophic risks, earthquakes. Hurricanes where insurance is either mandated with government backing or where government itself becomes the insurer of last resort. That recommendation was ignored. So when the transformers fail, when businesses lose weeks of revenue, when homes suffer damage from power surges, don't expect insurance to cover it. You'll be relying on disaster relief programs that weren't designed for simultaneous continent-wide catastrophes. Secret number 4. Government contingency planning is either classified or inadequate. In 2010, the US Federal Emergency Management Agency, FEMA, conducted a tabletop exercise called EarthX, simulating a severe geomagnetic storm impacting North America. The exercise revealed critical gaps in coordination between federal, state, and local agencies, inadequate planning for long-duration power outages, and insufficient medical, food, and water provisions for affected populations. The detailed after-action reports marked for official use only and not released publicly. Similar exercises have been conducted by the UK government and European civil protection authorities. The results are consistent. Existing emergency management frameworks are designed for regional disasters with functional infrastructure in surrounding areas that can provide aid. They break down completely when the entire hemisphere is affected simultaneously. Ask yourself, does your city have a published plan for maintaining water service, sewage treatment, food distribution, medical care, and public safety during a grid-down scenario lasting months? Most don't, because acknowledging such scenarios openly might be seen as fear-mongering or might expose the jurisdiction to liability if the plans prove inadequate. Secret number 5. We're spending more on asteroid defense than solar storm protection. NASA's Planetary Defense Coordination Office has an annual budget of approximately $150 million to track near-Earth asteroids and develop deflection capabilities. This is absolutely worthwhile. Asteroid impacts are real threats that we should prepare for. But here's the comparison. The probability of a civilization-threatening asteroid impact in any given year is roughly 1 in 100,000. The probability of a Carrington-class solar storm in any given year is estimated at 1 to 2%, 5,000 times more likely. Yet we spend 6 times more on the less probable threat. Why? Because asteroid defense is sexy. It's dramatic. It's the stuff of Hollywood movies. Missions like DART, which successfully deflected an asteroid in 2022, capture public imagination and generate political support. Solar storm protection is boring. It's installing capacitors on transformers, it's launching monitoring satellites, it's updating grid operation procedures. There's no dramatic impact to film, no clear victory moment, no Hollywood narrative. So it gets underfunded despite being orders of magnitude more likely to affect you directly. Dr. Mike Hapgood, a space weather researcher at the UK's Rutherford Appleton Laboratory, wrote in a 2019 article, "The most dangerous aspect of extreme space weather is not the physics we understand that quite well, but the psychology. Because severe events are rare on human timescales, each generation treats them as problems for the future, until suddenly they're not. Here's what makes these secrets particularly disturbing. Every single one of them could be addressed with technology and resources we have right now. The L4/L5 monitoring satellites could be built and launched for less than $2 billion. Comprehensive grid protection would cost $1 to $2 billion for the United States alone. Strategic transformer reserves $500 million. Improved emergency planning and exercises $100 million annually. The total cost to properly prepare for space weather across all these dimensions would be roughly $5 to $10 billion, spread over a decade, less than 0.1% of annual useless federal spending, and trivial compared to the multi-trillion-dollar costs of the event we're supposedly preparing to prevent. The technology exists, the knowledge exists, the money exists. What doesn't exist is the political will to spend it on a threat that hasn't happened yet in the modern era. But hasn't happened yet is not the same as won't happen. And as AR4294 demonstrates, yet might be running out. Which raises an urgent question beyond the infrastructure and the policies, beyond the satellites and the transformers. What makes right now uniquely dangerous in the entire history of human civilization? We are living in what historians might call the narrow window, a brief period in technological history when we're uniquely vulnerable to solar storms in a way no previous generation was and no future generation needs to be. Let me explain what makes this moment so dangerous. Travel back 200 years to 1824. The Industrial Revolution is underway. Steam engines are transforming manufacturing. But electricity remains a laboratory curiosity. When the sun erupts, it produces spectacular auroras that people marvel at. But there's almost no infrastructure to damage. The Carrington event of 1859 was devastating, only to telegraph systems technology so primitive by modern standards that its loss, while inconvenient, didn't threaten the basic functioning of society. People still cooked with fire, still transported goods with horses and sailing ships, still communicated face-to-face or by written letter. A solar storm was a natural wonder, not an existential threat. Fast forward to today. Your alarm clock requires electricity. Your morning coffee maker requires electricity. The water flowing from your tap is pumped and treated using electricity. Your car's fuel was refined and pumped using electricity. The food in your grocery store was grown, processed, refrigerated, and transported using electrical infrastructure at every single step. Your job, your communication, your entertainment, your healthcare, your money, all dependent on systems that require continuous electrical power. We've built a civilization that cannot function without electricity for more than a few days. But we've built that civilization using infrastructure designed with almost no consideration of space weather threats. It's like constructing a city in a floodplain while assuming floods will never happen. Now imagine 200 years into the future, the year 2224. If we're thoughtful about development, that civilization will have learned from our mistakes. Their power grids will incorporate GMD protection as standard design elements. The way modern buildings incorporate earthquake resistance in seismic zones. Their satellite constellations will have built-in redundancy and rapid replacement capability perhaps even manufacturing facilities in orbit that can produce new satellites on demand. Their space weather monitoring network will have real-time coverage of the entire Sun, including the far side, with multiple redundant satellites providing days or weeks of warning before threats arrive. Their emergency management systems will have been tested through simulations and actual events, with stockpiles of critical equipment positioned strategically around the globe. They'll look back at us the way we look at cities built without fire codes or sewage systems, with a mixture of disbelief and pity that we were so obviously vulnerable yet did so little to protect ourselves. But that future civilization is hypothetical. You're living now, in 2024, in this narrow window where you're maximally exposed. And here's what makes it even more precarious. We're not just at any random point in this vulnerable period. We're approaching solar maximum. The Sun operates on an approximately 11-year cycle of magnetic activity. During solar minimum, the Sun's surface is relatively quiet. Few sunspots, few flares, few CMEs. During solar maximum, activity explodes. The number of sunspots can increase tenfold. Major flares become common. The probability of Earth-directed CMEs spikes dramatically. Solar cycle 25, which began in December 2019, is now ramping toward its maximum phase, the Solar Cycle Prediction Panel. A group of experts from NASA, NOAA, and international partners initially forecast that maximum would occur between November 2024 and March 2026, with peak monthly sunspot numbers around 115. But here's the thing, the Sun doesn't read our forecasts. Recent observations suggest cycle 25 is exceeding predictions. In 2023, monthly sunspot numbers regularly exceeded forecast values. The November 2024 count reached 154, significantly higher than predicted. Some solar physicists now believe maximum might occur earlier and be more intense than originally expected. Dr. Scott McIntosh, a solar physicist formerly at the National Center for Atmospheric Research, stated in a 2023 interview, solar cycle 25 is proving stronger than predicted, which shouldn't surprise us. Our predictive models are still relatively crude. What concerns me is that we're seeing this intensity increase during a period when our technological vulnerability has never been higher. What does this mean? Practically active regions like AR4294 are more likely to form during solar maximum. The probability of X-class flares and fast CMEs increases. The baseline risk of a major geomagnetic storm affecting Earth climbs from roughly 1 to 2% per year to perhaps 5 to 10% per year during the peak period. We're there right now, or very close to it. Think about the timing. The Carrington event occurred in September 1859 during the solar maximum of cycle 10. The March 1989 Quebec blackout occurred during the maximum of cycle 22. The Halloween storms of October 2003 during the maximum of cycle 23. Major space weather events cluster during solar maximum because that's when the Sun's magnetic field is most complex, most twisted, most likely to produce extreme eruptions. History suggests we should expect at least one major event per solar maximum. We've been fortunate so far in cycle 25. The May 2024 storm was strong but not catastrophic. But we're not done yet. Maximum extends over a period of months to years, not a single point in time. There are still months, possibly years, of elevated risk ahead. And remember, statistics don't care about recent history. The fact that we just experienced a significant storm in May doesn't reduce the probability of another one occurring. The Sun doesn't think, well, I already did one this year, better wait a while. Each active region, each magnetic configuration, each potential eruption is independent. AR4294 exists right now. R4299 just struck us twice. And there are regions forming on the far side that we can't even see yet. Here's a question worth pondering. Do you know anyone who lived through the 1989 Quebec blackout? Ask them what those 9 hours without power were like. Now, multiply that by weeks or months and extend it from one province to an entire hemisphere. That's the narrow window we're in, too dependent to survive without electricity, too unprepared to prevent the catastrophe. But there's another aspect of timing that makes this particularly precarious. The last true Carrington-class event occurred 166 years ago. That's longer than the typical recurrence interval suggested by ice core data, which shows major events roughly every 150 to 200 years. Statistically, we're not just in the vulnerable window, we're potentially overdue. Dr. Pete Riley of Predictive Science Inc. published a study in 2012 estimating the probability of a Carrington-class event striking Earth. His conclusion: approximately 12% chance per decade. That means roughly a 1 in 8 chance that sometime in the next 10 years before 2034, we'll face an event of that magnitude. Those aren't comfortable odds when the consequences include multi-trillion-dollar damage and potential societal collapse. Imagine boarding a flight if there was a 1 in 8 chance it would crash. You wouldn't. Yet we're collectively boarding that flight every day, and most people don't even realize they're on the plane. The narrow window exists because technology evolves faster than infrastructure resilience. We built the systems before we understood the threats, and now we're so dependent on those systems that upgrading them, taking major infrastructure offline for modifications, carries its own risks and costs. It's a trap of our own making, too invested to change easily, too vulnerable to ignore safely, too focused on immediate concerns to prioritize long-term risks, and the window is closing, not opening. Not because we're making it safer, but because the sun cycle is progressing toward maximum, and AR4294 is demonstrating that extreme configurations can and do occur. But even as the danger peaks, even as the window narrows, there's something happening that you should know about a real-time demonstration of just how precarious our situation actually is. Right now, as this recording continues, AR4294 is rotating westward across the Sun's visible disk. Each day, Earth's rotation and the Sun's own 27-day rotation period carry the sunspot complex approximately 13 degrees farther from the center of the solar disk as seen from our perspective. This matters because geometry is everything in space weather. When a CME erupts from a sunspot near the center of the Sun's Earth-facing disk, it can strike us head-on, delivering maximum impact. But as active regions rotate toward the western limb, the right edge of the Sun as we observe it, their eruptions become increasingly likely to miss Earth or deliver only glancing blows. By the time a region rotates past approximately 60 degrees west longitude, even a powerful eruption has limited probability of significant Earth impact. AR4294 crossed the central meridian, the imaginary line down the Sun's center, as viewed from Earth around December 3rd. As of December 9th, when the recent G3 storm struck from AR4299's eruption, AR4294 had already shifted toward the western hemisphere of the visible disk. Here's what this means. We have perhaps 3 to 5 more days while AR4294 remains in a position where a major eruption could strike Earth directly. After that, it will rotate onto the far side, where it will spend roughly 2 weeks invisible to our primary monitoring satellites. It might erupt spectacularly over there, building and releasing enormous amounts of energy, and we'd have no direct observation of it. Or it might decay quietly, dissipating its magnetic complexity without incident. Then, approximately 27 days after it disappeared, it could rotate back into view. If it's still active, if the magnetic structure has persisted and perhaps grown even more complex on the far side, we'll be watching it again. And if it's decayed or fragmented, we'll breathe a sigh of relief and turn our attention to whatever new active regions have emerged in the meantime. This is the rhythm of solar observation. Active regions come and go. Most are unremarkable. Some are notable. A few are genuinely threatening. And once every few decades, one emerges that reminds us how vulnerable we really are. But let's talk about what's actually happening right now, because this is where the documentary stops being about historical events and future scenarios and becomes about the present moment you're living through. The CME launched on December 6th from AR4294's M8. One flare arrived at Earth on December 8th, producing the G3 geomagnetic storm that NOAA predicted. Observers at high latitudes witnessed spectacular aurora's green curtains dancing across the sky from Canada, Scandinavia, Scotland, even visible as far south as northern England and parts of the northern United States. Power grid operators reported minor fluctuations but no significant disruptions. Satellite operators implemented protective procedures pointing solar panels edge-on to the sun, powering down non-essential systems and reported no major anomalies. High-frequency radio communications experienced some degradation, particularly over polar routes, but nothing catastrophic. In other words, the system worked. The forecasts were accurate, the preparations were adequate, the storm came and went, leaving behind beautiful photographs and no lasting damage. This is the reality for most space weather events. Even strong ones. The infrastructure held, life continued, and for most people, the storm was either invisible or a fascinating natural phenomenon to photograph and share on social media. But here's what you need to understand. This was a G3 storm from an M8. One flare from a relatively simple active region. The CME velocity was 143 km per second fast, but not extreme. The magnetic field orientation, when it arrived, was only moderately southward enough to cause strong auroras and some grid stress, but not the nightmare scenario of a sustained, strongly negative B's component that would maximize magnetic reconnection with Earth's field. Now scale that up. Imagine an X10 flare more than 10 times more powerful than the mate. 1. Imagine a CME velocity of 500 km per second, more than twice as fast, delivering more than 4 times the kinetic energy. Imagine that CME carrying a magnetic field oriented perfectly southward, maintaining that orientation for 12 to 24 hours as it batters Earth's magnetosphere. That's a Carrington-class event. That's what AR4294 is potentially capable of producing. And the difference between a G3 storm that produces pretty lights and a G5 storm that destroys infrastructure isn't gradual, it's exponential. The most extreme events don't just cause more damage than moderate ones. They cause fundamentally different kinds of damage at fundamentally different scales. Dr. Tsuratani and Dr. Lakina, researchers who have extensively studied extreme space weather events, published a paper in 2014 stating, "The difference between a strong storm and an extreme storm is not just quantitative, but qualitative. Extreme events involve physical processes such as sustained periods of intense southward IMF that push systems beyond their design limits into regimes where normal operational procedures become ineffective." Have you been watching the auroras from recent storms? Maybe you've seen photos from friends at higher latitudes, or maybe you've been lucky enough to witness them yourself. They're beautiful, aren't they? That ethereal green glow, sometimes with hints of red or purple, dancing and shifting across the northern sky. But remember this, those beautiful lights are the visible symptom of Earth's magnetic field being disturbed. The more spectacular the auroras, the more violent the interaction between the solar wind and our protective magnetic bubble. When auroras are visible in the Caribbean, as they were during the Carrington event, is not a better light show. It's a sign that Earth's magnetic field has been driven into an extreme state that doesn't occur during normal conditions. The aurora is beautiful, but it's also a warning. It's Earth's atmosphere crying out as it's being bombarded by high-energy particles. And the fact that we can see auroras at unusually low latitudes means the magnetic field has been compressed and distorted so dramatically that particles are penetrating to regions that should be protected. So, yes, enjoy the auroras, photograph them, marvel at them, but also understand what they represent: a star 93 million miles away reaching out across the void and touching our world with enough force to make our atmosphere glow. It's magnificent and terrifying in equal measure. As AR4294 continues its westward migration, scientists are monitoring it constantly. Every 12 seconds, the Solar Dynamics Observatory captures new images across multiple wavelengths. Ground-based observatories track its magnetic evolution. Forecasters analyze the data, looking for signs of imminent eruption, rapid magnetic shear development, filament destabilization, increased flaring activity from smaller active regions within the complex. The analysis is ongoing, the watch continues, and the question remains: will AR4294 erupt while still facing Earth? Or will it rotate quietly out of view as of this recording? The active region remains magnetically complex, but has not produced the major eruption that its beta-gamma-delta configuration suggests is possible. Each hour that passes without an X-class flare is simultaneously a relief and a mounting tension. Because the magnetic energy doesn't dissipate, it either releases explosively or redistributes gradually, and we don't yet have the precision to predict which will occur. But whether AR4294 erupts or not, whether it threatens us directly or spares us, the broader implications remain. The Sun has shown us again that it's capable of producing dangerous configurations. The storms from AR4299 demonstrated again that our infrastructure is vulnerable. And our response has been again to watch, to forecast, to implement operational procedures, but not to fundamentally address the underlying fragility. So the question isn't really about AR4294 specifically. The question is about the next one, and the one after that, and the inevitable major eruption that will occur during one of these solar maxima, if not this one, then the next, or the one after that. Because one thing is absolutely certain: the sleeping giant will wake. It's not a matter of if, but when. And as we approach the final moments of this journey through solar physics and societal vulnerability, there's one more question we need to confront: what comes after? The monitors will keep watching, long after AR4294 rotates out of view, long after this documentary ends, long after you've moved on to other concerns in your daily life. Scientists at NOAA's Space Weather Prediction Center, at NASA's Solar Dynamics Observatory operations, at observatories scattered across the globe, will continue their vigil. They'll track AR4294 as it disappears over the western limb. They'll watch for any indication of activity on the far side: scattered light in coronagraph images, radio bursts, elevated particle counts that might suggest eruptions occurring beyond our direct view. And in roughly 2 weeks, they'll watch the eastern limb, waiting to see if the region reappears, still active, still dangerous, or whether it has dissipated into the chaos of the Sun's ever-churning surface. This is the reality of solar observation: constant surveillance of a star that operates on timescales both faster and slower than human attention spans. Individual flares occur in minutes. Active regions evolve over days to weeks. The solar cycle unfolds over 11 years, and the Sun itself will continue its fusion-powered existence for another 5 billion years, long after our species has either transcended or vanished. We are temporary observers of ancient, ongoing processes. The Sun was erupting with coronal mass ejections billions of years before the first human looked up at the sky and wondered what that bright disk was. It will continue erupting billions of years after the last human consciousness experiences its final thought. Our vulnerability is brief, a few centuries at most, during which we depend on technology that can be disrupted by solar activity. Before this window, solar storms were irrelevant to human welfare. After this window, if we survive and adapt, they'll be manageable nuisances rather than existential threats. But we exist in the window, right now. And what we do during this period will determine whether future historians describe us as the generation that prepared wisely or the one that ignored clear warnings until catastrophe forced our hand. So what can be done? What should be done? And perhaps most importantly, what can you personally do about a threat operating on astronomical scales? Let's start with the institutional level. What governments and utilities should be doing but largely aren't. The solutions are neither mysterious nor technologically impossible. They're expensive, unglamorous, and politically difficult, which is why they haven't been implemented. First, comprehensive grid hardening. Installing GMD blocking devices on high-risk transformers. Implementing real-time monitoring of geomagnetically induced currents. Creating strategic reserves of replacement equipment. And designing new infrastructure with space weather resilience as a fundamental requirement rather than an afterthought. Cost $5 to $10 billion spread over a decade for the United States alone. Compare that to the $2 trillion in damage from a Carrington-class event. Second, improved space weather monitoring. Launching replacement satellites for aging systems like DSQOVR. Establishing the L4/L5 observation points for far-side coverage, deploying additional chronographs and magnetometers, and developing better predictive models that can provide days rather than hours of warning. Cost $2 to $3 billion for a comprehensive monitoring network. The return on investment, in terms of damage prevented and lives saved, would be enormous. Third, enhanced emergency preparedness. Conducting regular exercises simulating long-duration power outages, stockpiling critical supplies, establishing communication systems that can function without electrical grids, and educating the public about space weather risks and appropriate responses, cost hundreds of millions annually. Value potentially priceless when the event actually occurs. These aren't radical proposals, they're cautious, conservative measures recommended by virtually every expert who has studied space weather impacts. The National Academy of Sciences recommended them in 2008. The UK Royal Academy of Engineering recommended similar measures in 2013. International panels have echoed the same conclusions, yet implementation remains fragmentary and underfunded. Why? Because the political incentives are misaligned. Politicians who spend billions on prevention measures that successfully prevent disaster don't get credit. Voters don't thank them for the catastrophe that didn't happen. But politicians who fail to prepare and then have to manage an actual disaster can at least appear responsive, competent, and action-oriented during the crisis. It's a perverse incentive structure that encourages reaction over prevention. And until that changes, until there's political reward for investing in resilience before disaster strikes, we're likely to remain dangerously unprepared. But you're not a utility executive or a government policymaker. So what can you personally do first? Understand that awareness itself has value. The fact that you've watched this documentary, that you now understand space weather as a real threat with quantifiable probabilities and preventable consequences that matters. Informed citizens can advocate for better policies, support politicians who prioritize infrastructure resilience, and demand that utilities and governments take space weather seriously. Second, consider personal preparedness, not paranoid survivalism, but reasonable precautions. During severe space weather events, power disruptions are possible. Having battery-powered radios, flashlights, basic food and water supplies, and a family communication plan doesn't require believing in apocalyptic scenarios. It's prudent preparation that's useful for any emergency, from solar storms to hurricanes to winter ice storms. Third, if you work in infrastructure, finance, emergency management, or other fields where space weather impacts are relevant, learn about it. Push for your organization to incorporate space weather into risk assessments and contingency planning. The more people within critical institutions who understand the threat, the more likely those institutions are to prepare appropriately. And fourth, share what you've learned. Not to spread fear, but to spread knowledge. The biggest obstacle to adequate preparation is the perception that space weather is either science fiction or someone else's problem. It's neither. It's physics, and it's everyone's problem. Dr. Mike Hapgood, whose work we've referenced throughout this documentary, wrote in 2019, "The biggest challenge in space weather preparedness isn't technical or even financial. It's cultural. We need to shift from a mindset where extreme space weather is someone else's concern to one where it's a shared responsibility requiring collective action. That shift begins with education and awareness." So here we are, at the end of this journey through solar physics, historical events, infrastructure vulnerabilities, and human fragility. The sun continues its ancient dance, magnetic fields twisting and snapping, plasma erupting into space, utterly indifferent to the tiny civilization orbiting nearby that has made itself vulnerable to those eruptions. AR4294 may erupt spectacularly before rotating out of view, or it may fade quietly, releasing its energy in small bursts or redistributing its magnetic complexity without major incident. Solar cycle 25 will continue toward maximum, producing more active regions, more flares, more CMEs. Some will threaten Earth, most will miss us, and eventually, inevitably, one will strike with the intensity that transforms our world. When that happens, and it will happen, whether next week or next decade, we'll discover how well we've prepared. We'll learn whether our infrastructure can withstand the assault. We'll learn whether our civilization is resilient or fragile. We'll learn whether the warnings were heeded or ignored. Until then, the sleeping giant breathes, somewhere beneath the sun's visible surface. Magnetic flux tubes are rising through the convection zone, building the active regions of next week, next month, next year. Some will be small and inconsequential. Others will be monsters rivaling or exceeding AR4294. One of them, at the precise moment when it's pointed at our planet, will erupt with catastrophic force. The question is whether when the moment comes, we'll be ready. The monitors will keep watching. The satellites will keep recording. The scientists will keep analyzing. And you, now armed with understanding, will know that when the auroras dance across unusual latitudes, when the news reports geomagnetic storms, when the sun reminds us who's really in charge, it's not magic, it's not mystery, it's physics, beautiful, terrifying, inevitable physics. And somewhere, 93 million miles away, the sleeping giant dreams of fire,